it's impractical to assume that everybody keeps updating themselves in a perfectly synchronous way. Okay. What is practical, on the other hand, is that there is some maximum lag that is allowed. Okay. So if you have not updated yourself for some time, okay, then too bad. You won't be able to engage in the secret handshake protocol with the members of your group. And we call that so there is some delta lag in our solution. And what we do, we translate all these key update messages so that essentially you can encrypt your challenge under all the information that is embedded in the key update messages. So it has the property that if you were not revoked in one of these key updated messages, you will be able to decrypt all that stuff. And if you were revoked in any of these key update messages, you won't be able to proceed. Moreover, also, this is a little tricky to do it efficiently, that if you were revoked now, but not before, so there's a delta lag, you will be able to proceed at the beginning, and then you will stop, and you will not notice what happened. Okay, and this is essential, because if you were freshly revoked, we don't want you to be able to tell that I am still in this group. Okay, so I'll be sending messages that have a delta lag, so you will recognize, you have these key update messages from this delta lag, and therefore you'll be able to consume them because you weren't revoked at that time. And it's a little tricky to do this so that, so that basically computation can proceed in this oblivious way to what's going on, and it's efficient at the same time. Okay, so it's efficient for the good guys, and yet oblivious for the bad guys who were revoked just now, and yet cannot make sense of it, that, oh, this is still my group, the group that I used to belong to. Okay? So we achieve this. However, we have definitely not optimal size of this whole thing. So our size is proportional to delta times log n. Log n is the number of your members of the group. Okay? So, this is, it's okay for small groups, and okay for some small deltas, but this can be definitely improved. And that's one of the open problems. And so I should stop here, and maybe there's still some time for questions. Maybe.
Is there any question?
Maybe just simple clarification. I'm not sure what I'm missing. But when you talk about the first approach, you said that you don't use elliptic curves in just like conventional cryptography and its standard assumptions, and it's more efficient. But my understanding was that elliptic curves provide the same security at using a group of smaller size as the conventional cryptography. So I'm not sure what.
Yes. So. That is true in the sense that we don't know of any attacks against them, but they are weaker. I should put it quote unquote. They are weaker in the sense that this is a relatively new assumption. So, moreover, the particular assumption that is used in these bilinear maps, it's a stronger thing. It's not just that discrete log is hard in the elliptic curves. It is that it's hard even though there is some special operations called bilinear maps, which can compute some a little bit magic properties, okay? And it is a stronger assumption to assume that discrete log remains hard even though you have special purpose elliptic curves which support these magic bilinear maps. And moreover, so this is a stronger assumption once you introduce the bilinear maps, which are required in the previous solution. Moreover, this is actually the computation of the bilinear maps. This is the costly operation. So while regular elliptic curve operations are comparable, the bilinear map, which is required in the solution, is like 10 times more expensive. At least currently, using current implementation. So that's why. They are not like, groundbreaking things, but yet, if you have a choice, you go for the one that is 5 times faster.